All right, here we are at the end of the semester. You're working on your last assignment and last lab, and we're getting ready for the final exam. So I do want to talk primarily about gravity, but let's do a quick review since we are right on the heels of the final exam. So answer this question. What did we learn? Think back over the semester and write down the 4 words that are most important, that capture the most important things we learned this semester, studied and learned. And then after you do that, add another 4 words. So pause the video, write down those 4 words, and then another 4 words. Think for a minute about what rises to the top of what we learned this semester. Hit the pause button and write down those words before you see what I'm going to write down. So the first list, I think, is obvious. We learned about motion. You can call it kinematics, but we learned how to describe and solve problems in motion. Then we learned about force and forces. Then we learned about energy, and we only spent a week on this, but this is an important subject. So these are the 4 most important things that we learned. And then if we wanted to expand that a little, we could expand the kinematics or the motion into linear motion and rotational motion. And the concept torque is a twisting force, right? So we learned about torque. And another very important thing that we learned was about vectors. So there are other things you might have mentioned: units conversion, scientific notation, some of that preliminary stuff. But if I were to pick 8 words, these would be the 8 words I pick. And why are we doing this? We're doing this because as we approach the final, we really want to be synthesizing and integrating what we learned. Okay, but anyway, we're here to talk about gravity. Gravity is primarily a force, but there's also energy associated with gravity. So we'll study the force part of gravity, and then we're going to look at the energy part of gravity, right? Gravitational potential energy. And gravity affects the motion, whether it's a ball that we throw on Earth, or a satellite orbiting the Earth, or the Earth orbiting the Sun, or the motion of galaxies and stars. That's all affected by gravity. So our last assignment integrates pretty much everything we've learned. Energy, force, and motion. The momentum part will be left out. Okay. All right, answer these 4 questions. Pause the video. Look at the 4 questions. I want you to answer all 4 of these questions. So pause the video and write down what a force is. List all the forces you can think of, or at least make as long a list as you can of naming the forces. Separate those forces into contact and non-contact forces, the ones you list here. Mark them as contact and non-contact. And the last thing is write down what we know about the relationship between force and motion. Okay? Integrating this idea of force and motion. What is a force? What's the relationship between force and motion? And what forces do we know about? So pause the video, do that, and then compare what you wrote down to what I write down. Okay, I hope you're not being lazy. I paused the video. If you just watch, you're not going to learn. You got to do, right? Learning by doing. So hopefully you wrote this down. Force is a push or a pull. And you get a push or a pull when 2 objects interact. That's our action-reaction. This is the 3rd law. The first law and the second law don't really tell us what a force is. It tells us how a force affects things. So the 3rd law, all forces are interactions between 2 objects. and it results in a push or a pull. And here are the forces that we're familiar with. The friction force, the symbols we use, the tension force, Ft or T, normal force, Fn or N, spring force, Fs, applied force, and gravity. Now notice that these are force types. This is not, friction. What is it? It's a general force. It could be tires on a road. It could be a person walking. It could be a person running. It could be a box sliding across. It could be any number of situations. But when two objects slide over each other and exert a force, we call it friction. When an object rests on another object, like a book on a table or a car on a road, we call that a normal force. But it includes all kinds of interactions. Applied force, what is that? It could be anything, right? Someone pushing someone pulling a chain. And spring force is pretty specific. It's a force when a spring interacts. And notice, and then there's the force of gravity, right? And what do we know about the force of gravity? At this point, we know that it's equal to mg. And this is the only non-contact force. These all involve the contact between objects. So first semester is called mechanics, right? These are mechanical forces. But the gravity force, which we've used right along and now we're going to study in detail, is in fact a non-contact force. If an object rests on the earth, the normal force is a contact force, but the gravity force is not. If you drop it from the air, it falls. Okay, I didn't answer question 4, so I'm going to pause and show you my answer to question 4. So this could be a question, an essay question on the final exam. The question would be, discuss the relationship between force and motion. And you would start with this equation, Newton's second law, and then you would identify everything in the equation. The sum of forces means the net force. It's a vector sum. And when we solve problems, because they're vectors, we always separate the x and y components. Mass in this equation means inertia, which is resistance to what? Fill in the blank. Resistance to change in velocity, resistance to acceleration, resistance to speeding up, slowing down, or changing direction. And acceleration is the change in velocity over time, or in terms of instantaneous acceleration, it's the derivative of velocity with respect to time. So that's Newton's second law. That's the relationship between force and motion. Force, acceleration, and inertia. And this equation is central to assignment 13. The force will be the force of gravity, and the motion will be the motion of the satellite, the planet, the orbiting object, or whatever the situation is. So this equation we'll use, but the force will be the force of gravity. So now we have to understand what the force of gravity is. Is it just mg or is it something else? So let's talk about the force of gravity. Perhaps true or not, the famous story of Newton and the falling apple. So interestingly enough, Newton was in London and a worldwide pandemic, Black Plague, hit. He went back to the country. He was trying to figure out the behavior of the planets, the reasons that the planets and celestial bodies move the way they did in circles. Things orbit other objects, and people wondered, at first they didn't wonder why, but later on they wondered, oh, objects don't naturally move in circles, so how do we explain that? And Newton's trying to figure out what is the force that makes the moon go around the earth or the earth go around the sun, and the story says, oh, the apple fell on his head, and he said, well, if earth can attract an apple, perhaps the earth can attract at a distance all those planets. And from that he formulated our current understanding of the universal law of gravitation. So up to now we calculate the force of gravity this way. We simply take the mass of the object and multiply it by 9.8 meters per second squared, and we get the force of gravity. But how about if we go away from the surface of the earth? Well, we all know now that the force gets weaker. And so this is only good on the surface of the earth. And if we want to know the force between any two objects, say the earth and the moon, then Newton formulated it this way, and this covers all situations of gravity, including us standing on the surface of the earth. So the force of gravity depends on the mass of both objects. They attract each other. And the separation between the objects squared, and the vector going from the object we're looking at, number one, toward the object causing the force on the first object. So this would be labeled F12 according to the textbook, right? And that's how that works. That's how that terminology works. So if we have the Earth and the moon, we simply take the mass of the Earth and the moon and the distance between them. And if we're looking at the force on the moon, then the unit vector would be that way. If we're looking at the force of us standing on the Earth, then it would be the mass of the Earth, our mass, and the distance between us and the Earth. And you say that's zero. No, we always have to measure. In the case of, this is for point masses, so in the case of larger objects, we always measure to their center. So the distance between the person and the Earth is the radius of the Earth. So watch what happens. Here's G, the gravitational constant. We didn't talk about that. There's the mass of the Earth, there's the mass of the person, and there's the distance between the two, the radius of the Earth. And then, so this is replacing, this is, in other words, rather than using mg, we're going to use the universal law of gravitation to find out what the force is on a person standing on the Earth. So taking this general universal law of gravitation expression to get the force between the person and the Earth, we collect the G, the ME, and the RE. Those are all constants at the surface of the Earth. And we put the mass of the person here, and it now has the same form as this. So the G, it's the mass of the person times G, so this is G. So if you take the numbers for the universal gravitational constant, the mass of the Earth, and the radius of the Earth squared, you better get it. No surprise. What you get is that this is equal to about 9.8, depending on the numbers you use. And the units now are going to be newtons per kilogram. And it turns out that newtons per kilogram, if you do it out, is in fact meters per second squared. So this, we say, is the value of G on Earth. If you go to the moon, what do we know? We know it's about 1/6 of that. And so what would you do? You'd put in G, the gravitational constant. You'd put in the mass of the moon, and you'd put in the radius of the moon squared, and you would get a number which is about 1/6 of this. So what's useful about this G is that it's the same for all people. It's independent of your mass. And so by using G, we can describe the strength of gravity. or what we're now going to call the strength of the gravitational field. And so this G becomes something very general and very useful. And so we can also say what it is it's the gravitational force on a person divided by the mass of the person. So if we take the gravitational force on any person and divide it by the mass of that person, we get on Earth the 9.8. But we can more generally define this G, gravitational field strength, as being something useful because it's independent of the person. So the force of gravity on a person on the Earth or the Moon is going to be smaller on the smaller person and bigger on the bigger person, but the G, the 9.8 on Earth and the 1.6 something on the Moon, is the same for all people. And so it gives us a sense of how strong the force of gravity is in any location. And it doesn't have to be just on the surface of an object. We can calculate G for any point in space. So now we've explained and introduced the concept of gravitational field. The general definition, this comes up in question 2, is the force of gravity per unit mass. So you measure the force of gravity, you use a second mass to do it, and you divide by that mass, and then you get a number which is independent of the mass that you're using. So we can think of the gravitational field as the space around any object such that it influences any other object placed there. So why is it, if we put a moon here, the Earth pulls on it? Every force that we experience except for gravity is a contact force. You don't push someone without touching them. So how does the Earth exert a force on the moon without touching it? It does it through this gravitational field. So we can picture that by these lines. And they're coming in because it's an attractive force. And just by looking at the picture, you can see that that force is going to get weaker when you go further away and stronger when you get closer. The field lines are coming close together. So a good analogy would be a light bulb, which gives out light. The light gets weaker as it goes out because it spreads out in space. So the gravitational field is spreading out in space and gets weaker as you get away from it. We can also picture the gravitational field around an object by vector arrows. These are sometimes called field lines. And you see if you're here, the force is 4 times bigger than here, right? Because it's r squared. That's what we call an inverse square law, that the force gets weaker as 1 over r squared. And so these are ways of picturing the gravitational field. So think that a mass isn't just located there. It has attached to it a field which surrounds it. And any object placed in that field is going to be subject to a force. And the force, of course, will be proportional to the mass that you put there. But if you divide the gravitational force by the mass you put there, you get this constant value for the gravitational field, which you can calculate for any object this way. So this is an important concept. It's going to be central to what we learn next semester when we talk about electric fields and magnetic fields. And it explains how non-contact forces work, which otherwise would appear to be magic. There is contact, right? The contact is between the object and the field. It's not in contact with the... Another way that people have come to think about gravitational field is if you imagine space as a two-dimensional space, for example, is a piece of rubber stretched over a hoop, and you put a mass on the rubber, it distorts the rubber or the space in a way that creates a force field. Let me show you a picture of that. So we can think about field also as the influence an object like the Earth has on the space that it lies in. And so here you have this image of gravity distorting what would otherwise be like just a straight flat space. And by distorting the space around it, it creates a situation where anything that comes into the space, it affects the motion. So if you imagine this forming kind of a vortex, that an object under the influence of Earth, like the moon under the influence of Earth, will naturally move in a circle because of the way that space has been distorted by the mass. So that's another way of imagining this concept of gravitational field. Okay, now let's shift and talk about energy. So we know about gravitational potential energy. Remember, we use the PEG a lot, but it's UG is the more common term. And it was simply the mass times G, makes sense, that's the gravitational field strength, times the height to which we lift it. So if you lift an object and drop it, it hits the ground with a certain amount of energy. If you lift it higher and drop it, it hits with more energy. And the higher you lift it, the more energy it has. But once we leave the surface of the Earth, the gravitational force in G is no longer constant. And so we need a new, more general way of calculating gravitational potential energy. So think about this imaginary case. Here's the Earth. It's not spinning, it's just sitting there. And somehow we're able to lift this mass, let's just say it's a 1 kilogram mass, high above the Earth and drop it. It will fall to the Earth and it will lose, there'll be a change, a loss of gravitational potential energy, which will become kinetic energy. Right? It'll move faster and faster and faster. And of course, once we're off the Earth, there's no up and down. If I release it from the same distance here, it's going to do the same thing. Or from here, it'll do the same thing. It always falls toward the center of the Earth. But now I place an object twice as far away. So if this is a distance r, let's just say that this distance is 2r. So is the gravitational potential energy the same? More? Less? Well, obvious it's more, right? The higher you or further away you drop it, the more gravitational potential energy it's going to lose and the more kinetic energy it's going to gain. But if it's twice as far away, is it double? Is it 4 times as much? And it turns out it's neither. So how do we calculate? We can't use mgh for this because the g, or the force of gravity, is not constant. So the way to understand how much energy is here is we would take an object. Let me erase this. So going back to a simple example we're familiar with, we take a 1 kilogram object on the floor and we lift it onto a table that's 1 meter high. So how much did the gravitational potential energy change? Well, we know it's mgh, but how do we get it? Well, the change in gravitational potential energy would be the work we do to lift it. And the work we do to lift it would be the force times the distance. They're in the same direction, so the cosine, remember there's a cosine, that's 1. The force times the distance. And so the force for 1 kilogram would be 9.8 times the distance. And so the force times the distance, or the force is mg, and the distance is h, and that's where we get the mgh. So similarly, if we want to know what's the gravitational potential energy here, we have 1 kilogram on the surface of the Earth, and we want to lift it 1,000 meters above the surface of the Earth. So we would just calculate the work it takes to take a mass here and move it to far away. And that would be the force times the distance. But as we move it, the force is not mg because g is not constant. The force is the mass of the mass of the Earth, the radius, the distance squared times g. But this distance is changing, right? So the force is changing. So you may recognize this. In this case, the work, which we learned early in the semester, and now you know what the integral is the integral of f times the displacement vector times the cosine of the angle. And you have to integrate because the force is not constant over the distance. So if you understand integration, what you understand is that you're calculating the work in small steps. And when you do this, you come up with the expression on your equation sheet for change in gravitational potential energy, and it looks like this. So doing the calculus integration, I'll ignore that detail right now, we would get that the change in gravitational potential energy is the final energy, G m1, m2, this comes out of the integration over r final squared. Notice it's r final, it's not squared. And you subtract from that the initial. So what happened to the r squared? That comes out of the integration. We won't worry about that right now. But this is the the equation you can use to calculate a change in gravitational potential energy. Now you'll notice in this case, this is a smaller number. We take it further away. So this is going to end up being negative. So sometimes this will confuse you, but we have to take the negative of this if we're going to have to change, if we actually want to calculate the increase, because the further away from the Earth the object is, the more gravitational potential energy it has. So this is the equation you'll use for any problems involving gravitational potential energy. And you'll notice that our initial at the surface of the Earth isn't 0 for this problem. It's going to simply be the radius of the Earth. And so what you can see is, as you get closer and closer to an object, the gravitational potential energy increases, and that's why we have a negative sign, because it should be actually decreasing. And there's a reason for that. So we can apply this to problem number 6 in the assignment on escape velocity. And escape velocity is simply this. If you throw a ball up, it goes up and it comes back to Earth. And if you throw it a little higher, it stays up for longer but falls back to Earth. And the higher you throw it, the longer it takes to get back. But it always comes back, but it won't always come back. If you throw it fast enough, and it turns out this is independent of mass, it will just keep going. Now, if you throw it with enough energy to just barely escape, in other words, it goes, but it's slowing down and it just escapes with basically 0 velocity at the end, then you have exactly enough energy. So you're turning gravitational potential energy, or the change in gravitational potential energy, has got to be equal to, in magnitude, to the change in kinetic energy. So the kinetic energy at the surface has to be equal to the potential energy at the end. But how much potential energy does it have here? Well, it has 0, right? Because if the ball is here and you drop it, nothing happens. So this leads us to the odd fact that the gravitational potential energy is actually 0 at infinity. And if you look at the equation, G m1 m2 over r, it's consistent with that equation that we saw earlier, that if r equals infinity, this is 0. But if this is 0 and this is gaining kinetic energy, right? And it's losing potential energy to gain kinetic energy as it falls. What does that mean? That means that the potential energy at the surface of the Earth or any other place than infinity is a negative energy. And so that leads to this odd and often confusing fact that gravitational potential energies using this are always negative. And so when you go from a big negative number at the surface of the Earth to a less big negative number here, that change in energy then ends up being positive. Okay, so that's some mathematical detail. Now let's go back and figure out what is the escape velocity. How much kinetic energy do you need to escape the Earth's escape the Earth's gravitational potential energy? So let's see how that's done. It's explained in the other video, but I'm going to go over it again. So what we need is a gravitational potential energy at the surface of the Earth to be equal to the kinetic energy, because the kinetic energy at the end is going to be 0, right? We want just enough energy to escape, and the gravitational potential energy at the end is going to be 0, because we said that's where it's 0. And so what we have is we need to start with 0 energy. Does that seem odd? Yes. This is going to be a negative number equal and opposite to this as a positive number. But we don't need to worry about that detail. We just want 1/2 m v squared at the surface of the Earth where we're launching it to be equal to m1 m Earth. The 1 is the object we're throwing. Oh, there's the g, divided by where we start, the radius of the Earth, and it's not squared. So if we have this much potential energy, we need that much kinetic energy to escape. And notice that the mass of the object is on both sides of the equation, so it cancels out. And if we multiply both sides by 2 and take the square root, that is our escape velocity. It's simply 2g mass of the Earth, that's for the Earth, over the radius of the Earth, square root. And notice, this is the escape velocity for Earth, but supposing we put in the mass of the Moon and the radius of the Moon, or the mass of Jupiter and the radius of Jupiter, or the mass of the Sun and the radius of the Sun, we can figure the escape velocity of any astronomical body. And if you do this for a black hole, guess what you'll get? You'll get an escape velocity larger than the speed of light, and that's why it's a black hole, because nothing can escape it. So there you have it. Force, field, and energy. And those are the tools you need to do the assignment and the lab. Let me just summarize. Okay, last but not least, our table of contents of what I covered in this video. So this is mostly on gravity, but the first 9 minutes is a good general review and overall synthesis of what we learned over the course of the entire semester.